Okay, cosmetics, and this one's a little touchy, but it is the reason that we don't look like this anymore when you put on sunscreen. So even though they went kind of fancy in the 80s and made it colorful, you still had to have the zinc oxide nose when you went out to the beach, and that was because here is just an assemblage of different size particles. When you put on this sunscreen that has this distribution of different size particles, the light that goes and hits against it actually scatters, so you can see it. Okay, that's what makes it visible. If you replace these particles in there, these larger size particles and stuff, with nanoparticles, what you're then actually going to perceive is the skin below it, because you're not getting any scatter by these particles here. Okay, and I didn't have any numbers for what the U.S. cosmetics industry has spent in nano. But I know that most cosmetics are now moving in that direction, whether they admit it or are using it as a promotional thing or not. But in Thailand, they've contributed $1.2 million over the last year into cosmetics with nanotechnology. Okay, nanofoods. Now, nanofoods are not. Let me put this up here, okay? They're not atomically modified food, and they don't have to be food that's produced by nano machines, okay? So it's really generally broadly described as when nanoparticles or nanotechnology techniques or tools are used in either the cultivation, the processing, the production, or the packaging of food. So that's a pretty broad term, but that's what we're talking about for nanofoods. So we're really looking at food packaging, food processing, and those types of things. And these are already on the market. Okay, so you can buy silver nanoparticle impregnated containers for food packaging for sterility. New processing where you get smaller emulsions of oils. Okay. Some supplements have come out of nano just because of the increased uptake of those products that are in there then. And nano herbicides and nano pesticides are kind of on the horizon for improvements to the current pesticides and current herbicides that we have. Okay, so USDA over the last year spent about $8 million in the food products realm. Engineering, of course, there are a lot of applications. Here's the smallest Beavers logo ever made. Okay. It was made at OSU, and it's 7 by 10 microns, so it's like smaller, about as small as a red blood cell. Okay. Pretty cool. Okay. But one of the things here is looking at alternative energies. So the next generation of solar cells where you won't have a particular solar crystal that just picks up one or all of the wavelengths and then wastes a lot of that energy. You would have them specifically tuned to pick up one particular wavelength and maximize the energy that could be captured out of that particular material. Okay, and Department of Energy has put in about $337 million over the last year. In the environmental, looking at remediation and things like green energy and more efficient manufacturing, nanotechnology has a lot of applications here. So for remediation, we're looking at some zero-valent iron, which are nanoparticles here that are just encapsulated in a droplet, and you can input these into a system that has anything that's chlorinated, any organic chlorinated compound that needs to be broken down. This could be there and assist in doing that. We're also building low-level detections for toxic agents, the swipes that you can do at the airport, those type of things for explosives and such. And EPA and NSF coupled up have put in about $521 million over the last year. So with all these applications, okay, and you can let your mind go wild. Really, it is the I want technology. It's forecast that this particular technology or suite of technologies is going to have annual sales roughly over $2.5 trillion by 2014. And so with all these applications, there's obviously going to be increased risk of exposure or increased risk of you running into these nanomaterials either in products or in the environment. So there is this potential then for large-scale impacts.
Am I reading this correct? You're predicting $2.6 trillion in sales in the next 2 years, but you don't have the testing mechanisms available to test these things because it's a new technology and it's not available for test.
And who's going to be selling it? And who's going to be, what's the selling about?
There's already over 1,000 products that are on the market that have nanotechnology or nanomaterials in them.
In which fields? I mean, which subgroup?
Predominantly health and fitness. But we're talking about some of these things you don't have to worry about, like a new tennis racket that has nanoparticle or carbon nanotubes, lined throughout it, but it's in a composite. So really, what's your risk of getting exposed to that and it being toxic? Okay, so there are, higher risk things and lower risk things. The bottom line is just about every industry sector, so health and medicine, all the ones that I just showed you, are moving in this direction if they don't already have products available in this direction.
Is the biggest applications defense and then health?
Right now. That's the biggest influx of government support, government funded.
Yeah.
So, yeah.
Dr. Harper, if I might ask a question. We're talking nanotechnology, and it's really break down cells to everything to get to the nano portion of it. Is that not what we all are? We're made up of bunches and bunches and bunches
Of things at the nanoscale?
Yeah.
Well, yes, we don't think of that as nanotechnology, so we're focusing in on those ones that can be engineered and tweaked and yeah. So those are the ones we're going to focus on. But yeah, there are a lot of things and a lot of biological entities and a lot of naturally occurring nanoparticles. Viruses, viral capsids are a good example of that. Okay. So we know that there's going to be widespread applications. It is the I want technology, and it's very exciting. I go to these engineering conferences and I'm just blown away. But I feel like I'm the toxicologist in the background going, but is it safe? And they don't know, and they aren't caring to test some of them. Now there's been a much more of a movement towards the middle where we're starting to merge the engineers and the toxicologists, and they're starting to work hand in hand to figure these things out up front. Because if we can design the material to be optimally, have the optimal performance we want, if we know what features of that make it toxic, we could potentially engineer those out too, right? While we're improving the performance, we could be decreasing the hazard of those materials to begin with. And that's kind of where my whole direction of research has focused. But I just got sidetracked for a minute here. So with these applications, we're definitely going to have large-scale impact. So what we want to know is, are the products that they're going to make with nanotechnology, are they going to be harming? Are they going to harm humans or the environment in ways that we don't foresee right now? Or will the manufacturing processes that are used to make these nanoparticles generate these new hazards and these new waste streams that we're not familiar with? So we'll look at some of the implications and get at some of the complexity of trying to get at what I see as the underlying holy grail is figuring out what properties or what features of the material we need to tweak to make it high performing but still safe. So the implications for nanotechnology stem from that we know that these materials are so cool because they have all these unique properties. They have all these novel properties that we haven't seen in other materials before. But right now, how they interact with biological systems, whether they're harmful or beneficial, has been under-tested. There hasn't been much studies done in this particular area. And without that data, it's really impossible to say what true risks are. But even if all the materials that we tested were completely benign, they were just safe as could be and much better than any chemical alternative, there is still the importance of public acceptance and perceptual risks that this is a new technology and that it's untested and those types of things can also hinder support and progress for this new technology that could have all these beneficial applications. And activists are already making the case that we're being exposed, and we are, being exposed to untested nanomaterials. And this next slide, I hope I don't offend anybody, I put it in for my father-in-law here. But this is kind of what the activists have been up to. So remember Feynman saying, remember his key talk, there's plenty of room at the bottom. So no testing, no nano is where they're coming from. And this was from the Nano Commerce in 2004. So the activists jumped on this right up front. The new technology and testing it. And so that there is this importance in this, this other side when we're talking about nanotechnology, that we do have all these applications. We also have to be very cautious when we're looking at these. But to me, the best thing about nanotechnology is that we can make things safer, that we can make things better, that we can make them more efficiently. And my take on this is we can do this, as being the toxicology side of me, can do this by working hand in hand with industry who's in the process of developing these new materials. Okay? And we can give them feedback on what the toxic potential of the materials that they gave to us, what that was. And then they can make an informed assessment about how to protect their workers that are in there and how to make sure that consumers that get the end product are not exposed in any way to a hazard that might be associated with it. This is also important for new biomedical applications, looking at the desired properties. Do we want it to target right to the cancer cell? Yes. Okay, does it do that? Yes. Okay, so guiding the development of safer nanomaterials is kind of what I have been working on for the last 4 years. And so I want to tell you a little bit about the investigations and really the complexities with studying chemicals, but now the added complexities when you start looking at nanomaterials. So for nanomaterials, we're starting in an information void. We have very poor data, very limited data, but we do know that of the data that we have that some of these materials act in very unique ways, are taken up by organisms in unique ways, and can impact organisms in unique ways. But we don't have any baseline for studies, okay? And a lot of the testing protocols, like I said, some of our standard testing protocols that we've relied on for looking and assessing chemicals, sometimes they don't work for the nanomaterials. So literally we have to go back and test the protocols to make sure that they're predictive of what we think they are before we can even use them to start studying what the impacts of the nanomaterials might be. And then here's kind of the added complexity with the nanomaterials, okay? We need to understand, all of these different features that you can change on a nanoparticle. We need to understand which ones we need to tune to make them safer, okay? So just a trivial little thing, because you can just tune any number of things in any exponential way that you want.